Hello students, I am back again. In previous lecture we have studied about the steps for calculating the one-way slab. So today we will design one slab. Okay, as we have studied in the previous lecture the steps. Going through that we will design the one-way slab. So are you ready? So here I have given one example that the slab for the roof of office building, which is 3.2 meter by 9.2 meter. Which is 3.2 meter by 9.2 meter. Resting on 300 mm thick wall. Live load is 2.5 kilonewton per meter square. M20 Fe415. Okay, as I said that the bigger dimension is Ly and the smaller will be Lf. So our slab will be like this. So this will be Lx, 3.2 meter, and this will be Ly, 9.2 meter. If you have mentioned nothing, then it will be the clear dimension. Okay, if you have not mentioned effective span or anything, then this is the clear span. Clear spans means center to center distance. So our slab, the distance will be like this. Okay, this is 300 mm brick wall. Means 0.3 meter brick wall on which the slab is supported. Okay, now the main thing was we need to calculate AST. For AST we need PT. For PT we need moment. For moment we need load, and for load we need size. This is the basic criteria. We have to reach here from here. So starting with the size, the step 1 was effective depth. Before calculating the effective depth, we need to decide whether our slab is one-way slab or two-way slab. So for that, the condition was that Ly by Lx should be greater than 2. So here our Ly is 9.2 and Lx is 3.2. So the value of 9.2 by 3.2 is 2.875. which is greater than 2. So our slab is one-way slab. Okay, so we will design our slab as a one-way slab. Now, the calculation of effective depth. So, as I said earlier in the previous lecture, that the effective depth depends on the span by depth ratio, which is L by D. And it is simply supported, so the value will be 20. Okay, for cantilever it is 7 and for continuous it is 26 into MF, modification factor. L means clear span. L means clear span. So the equation will be, we have to find depth. So D is equal to L by 20 into MF. So MF will be found from the page number 38 chart. Okay. IS 456 2000. Let us assume the percentage of steel point this is our IS code. Okay, so this is our chart, page number 38. The horizontal value will be percentage of steel, the vertical will be MF, and the chart of the FS. So let us assume the percentage of steel 0.6%. Okay, and Fs is equal to equation 0.58 Fy into 1. Okay, so 0.58. Our Fy as per given in the question is 415. So the answer will be 240.7 Newton per mm square. So suppose our graphics like this, and our 0.6 is here, and this much line are going. So as per the graph, the second line is our 240. So from here, at this point, the horizontal line will show the value of MF. So what is the horizontal line? So 0.6 and 240. So it will be something 1.14, yeah, 1.15 we can take. So here it will be 1.15. So our MF is equal to 1.15. Okay. I hope you all understand that from graph how to take the value. Okay. 0.6 value will be not given. Here it will be given 0.4 and directly it will be given 0.8. So you have to assume that this is the 0.6. Okay. 0.2 gap is given between the two vertical lines. Okay. So we get the value of MF is equal to 1.15. Now putting this equation in here, so we will get the effective depth. So L is 3.2, so we can write it 3200 mm, and here 20 into 1.15. So the effective depth we will get is 3200 divided by 20 into 1.15. 139.13. We can assume it as 150 mm. I hope you all understand this. Okay, because the round figure we have to take. You can also assume 140 or 145. Okay, but not less than this one, 139. So the effective depth we get it. Now calculate the overall depth. So overall depth is equal to the section will be like this one. Okay, here the diameter is being provided, main reinforcement. There are two types of diameter, 8 mm and 10 mm. We will take it as a 10 mm diameter for main reinforcement. Okay, the effective depth is from here to the center of here, which is 150 mm. So here the diameter by 2 and the clear cover is 20 mm. So total depth is equal to, effective depth plus diameter by 2 plus clear cover. So it will be 150 plus 10 by 2 plus 20, which will 175 mm. So the overall depth we get is 175 mm. Okay, so our slab overall depth is 175 mm. Okay, so this portion we have completed. Now this portion we have completed. Now coming to another size portion, which is effective span. This effective span. So write it here that we get the effective depth is 150 mm and overall depth is 175 mm. So effective span. There are two conditions for effective span. First one is clear span plus effective depth, which is 3200 plus 150, which we will get 3350 mm. Okay. The second condition is center to center support distance, which is 320, and the support is of 300 mm. So it will be 150 here and 150 here. So plus 150 plus 150. So the total depth will be 3500 mm. So smaller is 3350. That's why effective span will be smaller of both. So LEX is equal to 3350 mm. Okay, which is V here, like this. It is the length of the reinforcement. So this portion we have completed. Size. We get depth and effective span both. Moving towards the another step, which is load calculation. Which is load calculation. So step 3. Load calculation. So in load calculation there are 3 types of load: dead load, live load and floor finish load. So first one is dead load, which is nothing but the self weight of slab. So self weight of slab we find by the size into density. So here we are taking the width of the slab B as 1 meter, not as 9.2. We are taking one strip. Of 1 meter. Okay, so the size will be here is equal to B into capital D into gamma, and this is the RCC. So the density of RCC is 25. So B is equal to 1 into D is equal to overall depth 175.175 into 25. So the dead load is 0.175 into 25, 4.375 kilonewton per meter. We have taken all the dimensions in meter. Why? Because the density of concrete is kilonewton per meter cube. Now second, floor finish, here it is not given, so we can consider at 1. So floor finish is equal to 1 into 1. This is B into 1, means 1 kilonewton per meter. And live load we have given in the question, it is 2.5. So live load we consider 2.5 into 1 is equal to 2.5 kilonewton per meter. Suppose that in the exam, if in question it is given that consider the 0.8 meter strip. So at that time we need to multiply all the load with 0.8. Okay. So the total load is 4.375 plus 1 plus 2.5, which is 7.875. So this is the working condition that this much load is occurring. But for the factor of safety reason, we need to multiply it 1.5, which is factored load. So factored load is equal to 1.5 into 7.875, which is 11.81 kilonewton per meter, which we will consider to calculate the moment. So here we have completed this step also, W. Okay, so W, which is occurring on this beam is 11.81 kilonewton per meter. Okay, so we have got a W also. The third step, which is bending moment. Third step, we can also consider it as a fourth step. Okay, it is lengthy, but it is very much easy. We have to remind this step only. So bending moment. As our slab is simply supported and the UDL load is occurring on the entire span, so the equation of bending moment M is equal to WL square by 8. W is the load, L is the effective length. We will take it in the meter. So 11.81 into effective length 3.35 whole square divided by 8, we will get the moment. So the moment is 16.57 kilonewton into meter. Okay. Verify the calculation again. Okay, which is moment. Now we get the moment. So for calculation of PT, step 5, percentage of stick, PT. Okay, the equation of PT is equal to 50 FCK by Fy 1 minus under root of 1 minus 4.6 mu by FCK BD square. So the value will be 50, FCK is 20, Fy 415, 1 minus under root of 1 minus 4.6, mu will consider into Newton into mm. So 16.57 into 10 raised to 6, because our FCK value is in Newton per mm square. 20 into 1000, V is equal to 1 meter strip, so 1000, and D square means effective depth means 150 square. So the value of PT is equal to 0.21%, which is greater than 0.12%. So okay. 0.10 is the PT minimum for Fe415. So we get the value of PT. This step also completed. Now the last step, which is AST. So the equation of AST is reinforcement. In reinforcement, the first one is main reinforcement, which is in longitudinal direction. The equation is AST is equal to PT BD upon 100. So PT is equal to 0.21 into 1000 B into 150 D upon 100. So the value of AST is 320.3 mm square. Okay, now calculating the spacing. So spacing is equal to small AST by capital AST into 1000. So we have considered 10 mm diameter as a small AST. So small AST is equal to pi by 410 square. Okay, so what will be the value? 3.14 into 10 divided by 4, 78.5. So here 78.5 divided by 320.3 into 1000. So the spacing is 245 mm. Okay, 245 mm. So we can provide it as 240 mm center to center. You have to decrease the spacing. While in other cases like AST, you have to increase the value. Because as possible you are decreasing the spacing, the AST will be increased. And we need to provide AST in increasing value. Okay, that's why we are decreasing the spacing. So the main reinforcement are 10 mm dia, 240 mm center to center, which will be like this. So in between this, the spacing is 240. Okay, and the diameter is 10 dia. Okay, now the second reinforcement, which is distribution. Okay, so we need to consider minimum percentage of steel, minimum PT value. So for Fe415, PT minimum is equal to 0.12. So AST is equal to PT B capital D upon 100. As I explained you in the earlier video in the steps. So B is equal to 1000, D is equal to 175. Here in distribution steel we will consider the capital D, 100. So how much AST we get? So 0.12 into 1000 into 175 divided by 100, 210 mm square. And for spacing, small AST upon capital AST into 1000. So small AST we will consider of 6 mm dia, okay, for distribution. So is equal to pi by 4 6 square. So the value will be 28.26 mm square. So the spacing we get will be 134.5. We can say that 130 mm center to center. So the distribution steel is 6 dia, 130 mm center to center. Okay. So the distribution steel will be seen like this in the figure. See. It will be straight bar. The spacing between this is 130 and the diameter is 6 dia. Okay. So we can also make the figure here like this. See. From here it will start, here it will go, here it will go straight. So from here it will start, from here it will go, and here straight. Okay, these are the main reinforcement, which is 10 dia, 240 mm center to center. Okay, and the another one is distribution steel, which will be here. Which are 6 dia, 130 mm center to center. Okay, and the effective depth is 150 mm. Okay, I have said you earlier also that the figure considered 2 marks, so you need to draw the figure. Now let's check what the spacing condition. If the spacing is more, then there will be failure in the cracking. So check for cracking. So check for cracking. To prevent the cracking, the spacing should be less than the limiting value. So for main reinforcement, 2 conditions. First one is 3D, second one is 300, and third one is which we have calculated, which is 240. That we have calculated. So 3D means 3 into 150, which means 450. So the smallest, it should be less than 300. So this is okay. Okay. And the distribution steel, two condition. 4D is equal to 4 into 150, which is 600 and 500. But our is 130. It is less than 500. So okay. Okay. So I hope you all understand this sum. First of all, we calculate the effective span, then effective depth, then effective span, then load calculation. After that, we have calculated the moment, which we have by using the WL² by 8 equation, in which L we have taken the effective span and W which we have taken the load. That we have calculated in the third step, dead load plus live load plus load finish. After that, we calculate the PT, then AST, then spacing, and then check for the cracking. And then last is the figure. So you all have understand my sum, and for today this much only. In the next video I will come with another slab example. Till then, bye bye.